It's a real honor to be here, and I really appreciate for the organizers for asking me to give several talks because they're all my favorites, and I didn't want to leave any of them out. This is a talk that I actually haven't given very often, but as you'll see, it's a talk about the most valuable piece of research I've ever done. And when I say valuable, I don't mean in intellectual value, though it's got that, but just in terms of bucks. I mean, this piece of work, which I did back in the 90s, in the 80s and the 90s, I had no idea it would turn out to be valuable, but it's generated billions of dollars. And you'll see how and why. None to me, unfortunately. Okay. It's also what makes this an appealing talk, at least to me. It is this idea. It expresses I think, very well the idea that when we look at our bee colonies, they really are cognitive entities. We think of that is to say, things that can take in information, process it, make decisions, and take action accordingly. This is something we're familiar with at the level of ourselves and our pets, organisms. But in the honeybee colony, you see a whole society that is organized to take in information, process it, make decisions, and act accordingly, as we shall see. We're going to be focusing on how a colony allocates its foragers among food sources. It's going to have to go out into the environment, get the information, and then act on that information. This is a different perspective on the bee colony than we looked at yesterday when I talked about a colony as a honey factory. That was all about going out and getting materials, nectar, and producing a product, honey. This is a different one. This is actually part of the same process, but here we're going to be focusing not on the materials that the bees are collecting, but on the information they're collecting. Collects, just to repeat myself, I suppose, the colony is going to go out, collect, and use information about patches of flowers. And again, the key problem that the colony has to solve hour by hour, day by day, because it's an unending problem, how to allocate its foragers most efficiently and effectively among the various sources of nectar that are available. And we'll see that is an ever-changing palette of opportunities. So think about, to illustrate this matter, you can think of the colony as having an ensemble of foragers which can be deployed. And we're going to focus just on the nectar collection foragers, the nectar collectors. And there are various foraging sites out there in the environment all around the colony over great distances. And the colony has to solve the problem of how many bees descend to this patch of flowers, how many descend to that patch of flowers, how many descend to that patch of flowers. And then once it's got that worked out, well, a few hours later, the foraging opportunities change. Some patch of flower, one of those patches of flowers has probably gotten better, more profitable, one has gotten less profitable. So the colony has to has to resolve that problem and track the opportunities. I think you can see that this is a huge information problem because the information is widely dispersed and it's ever changing. And a colony to respond has to deploy thousands of individuals appropriately. That's what attracted me so much to the problem in the first place. How many people here have sat in front of a hive or lay on the grass in front of a hive, just looked up at it and seen the foragers shooting away? It's an amazing sight, isn't it? Those little girls are headed out, they know where they want to go, and you lose sight of them. And I just want to stress, this is a difficult problem. It's a dynamic problem because the flowers bloom and then they wither, so opportunities come and go. It's an unpredictable problem. The future availability of a patch of flowers is unknown. They have no idea whether that patch of flowers is going to be a strong source of nectar for a few hours or a few days. However, it does have a good, fairly simple general solution. If the patch of flowers is large and rich, has profuse production of nectar, the colony should allocate many foragers to such a patch of flowers. On the other hand, if it's a small patch of flowers with might have great flowers in it, highly productive flowers in it, but if they're not very many, or if it's not very productive, then they should send just a small number of foragers to that location. So the question is, how do they do this? Oh, I just wanted to illustrate the contrast or the way there are different possibilities. These are two photographs I took in a couple of springs ago, and I was speaking in Northern Ireland. I was walking around, and I saw, it was in March, I think it was, and the willow, the salix, was just coming into bloom. So we found this nice big pussy willow tree. That was pretty cool. And there was only a half dozen bees foraging on that. But nearby, there was a gorse hedge, and that had hundreds of bees on it. It was a bigger patch, and it was more attractive at that moment. So there, it's just a great illustration of, okay, this one should get a few foragers for now, and this other one, let's throw a lot of foragers at it. Now, what I want to do next is show you just how dynamic a colony's allocation of its foragers, its nectar, well, yeah, we'll focus on nectar foragers today, is among patches of flowers. And the way I did this is first of all, that's not me, that's a friend of mine. I built a large observation hive. It was an observation hive that was large enough to accommodate 8 frames of deep frames from a Langstroth hive. And actually, I didn't want to have it broken up into 8 separate frames, so I bonded together 2 frames to make 1 to 4 very long horizontal frames like this. Those are fun to work with. And so it's a big observation hive. And the reason I wanted it large is I wanted to have a hive, an obs hive. I love that expression you have here in England, obs hive. An obs hive that was large enough to accommodate a full-size colony. So that colony could hold 16,000 15,000, 16,000 bees. The bees would come and go down through this area down here. This isn't quite the entrance arrangement that was actually used. They came and went down here, and there was a little shunt down here so that when the bees came in, they were shunted to one side of the observation hive. So all of the bees that would do dances, all of the dances would be performed on one side of the hive. And as we'll see, those dances are all performed in the vicinity of the entrance. So this is what we call the dance floor. And so we can, and I put over the dance floor, I drew on the glass a sampling grid. And the way there would be multiple dancing bees at any one time. And this was before I had video technology, so this was all hand done, which is fine. It saves transcription work. So the procedure was I would use a random number system for choosing which square on this sampling grid to focus on. And I would so I'd go to that grid square and I'd see whichever bee was dancing most prominently. And I would take information with a helper. I'd record the information that's needed to determine the direction and distance to the flower patch that the bee is reporting on. So that requires recording the angle of her dance relative to straight up, and it also records with a stopwatch timing the duration of the waggle runs within the dance. And so we would go through record that information for at least 4 circuits of the dance. And we do that, record that, and then go on to the next bee. So it's just sitting there by the hive all day long, taking information on the pattern of dancing by the bees. This is what we more commonly used, and like what Heather talked about yesterday, is a 2-frame observation hive. But I show it because it reminds us of the distribution of where the dances are performed, where the dance floor is. It's just inside the entrance. And you can think of this dance floor as a place where the successful foragers come in and broadcast the news that they have to report about foraging opportunities. And in this same area, it's also where the unloading of the nectar is done, the unloading of the water, and the reception of the nectar, reception of the water. And it's also where the unemployed or idle foragers come down in the morning and hang out to get word about where to go out and forage. And one thing that's really important, I won't go through the evidence on this today, when a forager, an unemployed forager comes down to the dance floor area, she doesn't do comparison shopping of the dances. She chooses a dancer chosen at random to follow. And she gets the information from that dancer and then goes out of the hive. And I want to stress that random sampling by the dance followers, because it's critical to how the colony allocates its foragers. It's going to boil down to it's going to come down to how strongly the bees advocate going to this patch of flowers or this patch of flowers. That's how they get the adaptive bias of more bees to the best sites. It's not based on the dance followers sampling and comparing dances. It's based simply on the bees making their reports, adjusting the persistence of their announcement or advertisement of a food source. We'll look more closely at that. What I want to show you now is some of the results. I'll do it for just 4 days of the information that was collected by monitoring the dance activity in a colony of one of these large observation hives. And each of these, so these are diagrams. You'll notice the scale here goes out to 4 kilometers. There's a little bit, the bees the range of their foraging by the bees is actually, they'll go 10 kilometers or more. When I work in places where there's not, if I go up to Cranberry Lake Biostation, and I'll talk about that shortly, I've seen bees, they're desperate up there. There's not much food, but once I did see bees, they did find some food, and believe it or not, it was 14 kilometers away. And that in miles, so that's what, 14 times 0.6 is 8.4 miles away. So they will really go great distances. In the case of this study where I was doing it, this colony was set up in a forest reserve, which I'll talk about this afternoon, the Arnott Forest. They were typically going somewhere out to 4 kilometers. A few were going beyond 4 kilometers, and even that's a respectable distance. What's that, 2.4 miles? And what we can see is each of these dots represents the location indicated by a dancing bee at some point during the day. The black dots represent sites that were reported by nectar collectors, bees that came into the hive without loads of pollen and unloaded nectar. The colored dots indicate sources of dances performed by bees that were bringing in pollen. They may have also brought in some nectar, but they had just clear pollen loads, and the color of the dot indicates the color of her pollen load. And so what do we see on this day of the 13th of June? And this was back in 1981, I think. We see down in the southwest there, out between, looks like 2 and 4 kilometers, there's a lot of black dots. There was a big nectar source out in that direction. We also see up in the northeast, way out at 4 kilometers, we also see some black dots. So there was a nectar source way up there in the northeast. Closer to the hive, again in the direction of the northeast, we see some orange dots. So there were bees that were collecting and reporting on a rich pollen source to the northeast, less than 1 kilometer away. And swinging down to the southeast, we see southeast, we see yellow dots. So there was a good pollen source of yellow pollen to the south, not too far away. And then to the southwest, there's more black dots. So there was another nectar source to the southwest within 1 kilometer. So a number of sources were being tapped into by the colony on the 13th of June. And that's a summation for the whole day. Now let's look at the 14th of June. Things are a little different, but there's some similarity too. There's still going intense nectar collection to the southwest between 2 and 4 kilometers out. There's still the yellow pollen collection to the southeast within 1 kilometer. There's still that collection of nectar to the southwest within 1 kilometer. But strikingly, now there was a lot of dancing to the northwest, only about 0.5 kilometer away for a nectar source. Lots of interest. Something really became very profitable and evidently was sizable to elicit so much dancing by nectar foragers to the northwest. And there's a little bit still up to the northeast, but not as much of the orange pollen collection over to the northeast. So one day is one pattern, next day is a different pattern. Now let's compare the 15th of June to the 14th of June. Well, what do we see? Well, we see that now that yellow pollen to the southeast is still very important, that nectar collection to the southwest within a kilometer is still very important, but things are starting to fade to the southwest in that 2 and 4 kilometer range. And that area to the northwest, which was so heavily advertised the previous day, at about 500 meters, it's not getting as much advertising on this day. So every day we've seen is a little different. Let's look at another day, 16th of June. Now the 16th of June, the first 3 days I've showed you were days of ideal foraging, sunny and warm. 16th of June, cloudy, light rain. Familiar conditions for you folks. And look at what the bees have done on this day. They were not ranging widely from their hive. But not only were they not ranging widely, but they've tapped in again. They found this important source of orange pollen to the northwest again. That's very important. And again, they're collecting nectar, but it's close to the hive, only about 500 meters out. And in some cases, on this day, because they were working so close to the hive, we went out and we looked for that nectar source, and we found that there was an old field in the forest we didn't know about at that distance, hadn't found. And there was the bees were collecting, what was it? Oh yeah, it was just clover. There was clover down in the grass, and the bees had found that and were collecting from that. I don't know what the orange source of pollen was, but the key thing is it's a highly dynamic, these 4 illustrations we've seen just highlight the fact that it's an ever-changing, highly dynamic problem that the bees are solving. Just to compare all 4, to make that point even clearer, just we can see how different each day is from the next day and the day before. And we did this lots. we did this in 3 times that summer with 3 different colonies, and it was always a very dynamic pattern. And in August, which is one of our times of sparse foraging, the bees had trouble finding food, and they went way out of the forest, up to the northwest, out about 4 kilometers. And outside of this forest, there is one valley. The land in this forest area is very marginal for farming. It was abandoned from farming in the mid-1800s. But there is one valley nearby where there's actually decent soil. And the bees had gone out of the forest, flown out those several miles, and had found a patch of alfalfa, hayfield, which was in bloom. And so they had discovered that, and that's where they were going. So that was kind of fun to find. That was fun to find. So we've seen the problem. We've seen what they can do. We've described what they can do. But I've really just shown you the pattern. I haven't really shown you that they're actually solving the problem very well. And so let's address this question. How well, really, does a colony match its foraging efforts to the foraging opportunities? And again, here's the problem, schematically indicated. You've got these different patches of flowers. Each patches vary in their size, big circle, little circle, and their profitability. And what's the colony got to do? It takes in information about those patches of flowers, their profitability, size, takes it in, and then it has to generate a labor output, different numbers of foragers to each of those patches. The question is, how well does it solve that problem? Well, to test a colony's skill, I needed to be able to control a colony's foraging options, need to set up an experimental control of their foraging options, and I needed to be able to measure how many foragers are allocated to the different options. So I needed control. Had to find a place where I could control the foraging operation of a colony on a natural scale, not in a laboratory, but out in the field. So where do no, not easy to do. but fun. The way I do this is and this is where I first started going up to this really cool biostation up at Cranberry Lake. It's up in this vast state forest, national park, up in the northeast section of New York State. Here's New York City down here. And if you drive up about 7 hours, you'll get up to you'll get up to Cranberry Lake biostation area. Here's where I live down here. So it's only 3 hours for me. And this is a place, as Heather explained yesterday, this is a place with no flowers, basically no flowers, and no honeybee colonies. Because it's so heavily forested. There are bumblebees up there. It's not devoid of flowers. It's not devoid of sources of nectar and pollen, but evidently not enough to support the budget of the big budget of a honeybee colony. But it does enough to support bumblebee colonies. So one of the features of this place is it had virtually no flowers, so I could control the food supply. And it also had no other colonies of bees. So I could take up a colony of bees, or as we'll see, 2 colonies of bees for some of the experiments, and know that the bees that were coming to my feeders were coming from that colony or colonies. Now, what is the setup for the first experiment? What was the setup look like? Well, we take up this little portable hut. It's called the Orange Hut. Really original name, huh? And inside that Orange Hut we set up a 2-frame observation hive. You can actually see a little bit of it here. And it's kind of a neat little thing. It mounts, it hangs in the hive, so you can climb in and out of the hut and comfortably sit beside the hive. The reason we put the hive in the hut is we don't want light shining we don't want the bees to be able to see the sunlight. And so that means they will orient their dances by gravity. They're not influenced by being able to see the sun. So it makes it easy to read the dances or convert the dance information into direction and distance information. And it's a small observation hive because we're going to work with a small colony. We don't need a large colony for these experiments, but what we did need is we needed a colony in which every bee in the hive was labeled for individual identification. And that uses the familiar queen tags and dots of paint. And you can see just a little sampling of what that looks like if you take a look inside that hive. Every bee is become an individual, a recognizable individual, and it's great. And the reason we needed that, every bee labeled for individual identification, is because when we set up these experiments, we don't know which bees are going to be the star actors in this. So we have to have everybody labeled from the get-go. And we didn't want to futz around in the course of taking the data with trying to label the bees and things like that. So we labeled everybody at the beginning. And when we do this, we can keep the colony actually well labeled for several weeks because when we set up the OBS-Hive colony, we don't give them sealed brood. So there's going to be 2 weeks at least before any brood emerges, and so all of the bees in that colony are labeled for a period of study. I'm looking at those labels. Some of them are done better than others. Because, a 6 and a 9 don't look different unless you've got an orientation. So the labels were all supposed to be aligned with the bottom of the number at the bottom of the bottom of the thorax. And orange, green 98, she looks good. She's properly labeled. Yeah, orange, yellow, 48 is pretty good, but orange, yellow, 49, you have to twist your head a little bit. It's only the 6s and 9s that get you. No. Okay, all the bees are labeled. And then then we not only control the bees, we also control the food sources. So at this setup, we have the hive, and here's where the Orange Hut is. It's in the complex, it's in the campus, we call it, of the buildings at the biostation. It's an old forestry school. That's where the Orange Hut is. The H stands for hive. And then we train bees out to dishes of sugar water like this. This photograph was not taken from this experiment. These bees are unlabeled. but it shows the feeder, dish of sugar water, fill it with sugar water, invert it over a plastic plate which has grooves in it so bees can sip from the sugar water that it contains. And then we train bees out to these two locations, feeder north and feeder south. These are out, both are 400 meters out, same distance, but in opposite directions. So we're paring the problem down for the bees. We're gonna give them two food sources. But that's enough to test their ability to choose and allocate appropriately. Now, one of the things we're going to have to do is we have to keep track of how many bees are visiting each of these feeders, and we do a roll call every 30 minutes. And it turns out to be, I mean, you could write down all the codes and things like that, but it turned out to be much simpler. I found I could write all 4,000 color and number combinations on a sheet of paper, or not write it, but print it. So that's all 4,000 of the identification codes represented there. And so then I would have an assistant at each feeder, and he or she would just check off the IDs of the bees that visited the feeder during each 30-minute period. So isn't that cool? I mean, isn't that a simple, low-tech way to record the data? No video. It's so efficient. No batteries either. And one other thing I want to highlight about this data sheet, very important. You may not be able to see that, but the date there is the 4th of July, 1991. Now that's a national, that is of course our Independence Day, the signing, it's actually 2 days after the signing of the Declaration of Independence, but it's the celebrated day of independence from Great Britain. And it was called Great Britain back then, I checked, and appropriately so. So that's a major national holiday. So, but you can see, dedication. Everybody else at the biostation is goofing off that day, but not us. We had our bees, we had good weather, we go ahead. Now here's an example of what I mean by that shows the ability of a colony to skillfully allocate its foragers between nectar sources. So here's our little schematic representation. Here's our hive, here's our north feeder, here's our south feeder. It's 8 o'clock in the morning. We started this day by filling the feeders at 8 a.m. in the morning, actually a little before 8 a.m. This one is filled with a 30%, or 1 molar, which equals 30% sucrose solution, this feeder. The south feeder is loaded with a richer sugar solution, 2.5 molar, which is 65%. And at 8 o'clock in the morning, we had actually trained a couple of bees out to both of these feeders, but the previous day. But at that time, both feeders offered an intermediate quality food. And so on the 8 o'clock on this morning, there was just a handful of bees. So for the first 30 minutes between 8 a.m. and 8:30, 1 bee came to the north feeder and 0 bees came to the south feeder. But that eventually bees started coming to both of these feeders. And you can see that by noon, we just let the thing run. And every half hour, we recorded how many bees came to each feeder. And by noon, the time period between 11:30 and 12, there were just 12 bees visiting this north feeder with a relatively meager forage, but 91 bees had visited that feeder during the half hour preceding noon. So the colony had very sensibly, accurately split its allocation between the two. Both places provided food ad lib, but the food was much better here, so they sent lots more bees over here than here. Okay, they did well. And then we made life, challenged them again. We flipped things around. We swapped the location. So now this feeder to the north has the good stuff, the high test, and over here we give them actually even slightly poorer food than was here in the morning. And we can see that by the end of the afternoon, by 4 p.m., the bees have beautifully reversed their allocation. Now it's 121 here and only 10 here. And And these are actually the stable, by the time, we went for 4 hours before changing things, because these are numbers where it's stabilized. And you can see why it would stabilize out, because when you have 121 bees visiting the same feeder, they tend to build up and start to interfere with each other. And so even though it's very rich food, very profitable, it gets harder and harder. So it finally gets to a point where the profitability here, with this many bees exploiting it, matches the profitability over here. So this is how we could look to address this basic question. How able are colonies to skillfully allocate the foragers between nectar sources? And the answer is very well. And I won't go through the calculations, the energetic calculations, but on a per forager basis, they've equalized things for these two food sources with this distribution of foragers. So what do we learn from this? We can see there was both a skillful allocation and a nimble reallocation when the conditions changed. Very good, bees. Great. That was neat. The question is now, that's just what they did. Now we want to look at how they did it. What did the bees do to produce their allocation and then their reallocation? Well, this is where the analysis from the data sheets comes in, for deeper analysis of the data sheets comes in. What those bees did is they produced, their implementation to get those patterns was they produced correct rates of recruitment to and abandonment of the feeders. And from these data sheets, we can calculate this because we know when new bees are showing up at each feeder, and we're also noticing when bees are leaving, stop working at each of those two feeders. And what we found, and by recruitment, the unit of the measure of recruitment is recruits per 30 minutes per bee visiting the feeder. So it's a per capita rate of recruitment of additional bees to the feeder. That's the measure of recruitment. So that's an indication for each bee that's already working the feeder, how many more bees she brings in 30 minutes. And likewise, the abandonment is the abandonments per 30 minutes per bee visiting the feeder. And the bees get it, and here's what the bees have done. For this, in the morning, for this excellent food source, per 30 minutes, per bee that's already working the feeder, they were bringing 0.4 additional bees to the feeder. That's the average recruitment rate during the morning. And their abandonment rate was very low. It was almost zero. 0.04 bees were abandoning per bee per 30 minutes. And so these arrows represent the ratios of those things. And if you've got a high rate of recruitment and a low rate of abandonment, the numbers increase. Over here, the recruitment was very low, 0.01 bees per 30 minutes per bee. And that's basically zero. And the abandonment was basically zero. So the numbers didn't change from the starting point, because we actually had, I guess it was about 10 bees pre-visiting that feeder at the beginning of the day, both of these feeders. So that's what they did. They didn't have to count other bees at the feeder. They didn't have to do anything like that. The bees, as we'll see, they just went to that food source. They assessed its goodness by some measure that is still a little mysterious to us. They got some sense of goodness of going to that food source, and they either recruited for it by performing waggle dances, or they abandoned it. And then when things changed in the afternoon, things really change in terms of recruitment rate and abandonment rate. At this feeder, which is now went from being so good to being so poor, the recruitment drops from 0.40 to 0.01, and the abandonment skyrockets from 0.04 to 0.27. So there's a mass exodus from this of bees quitting the use of this feeder, and what we see over here now is this high rate of recruitment, like was here in the morning, and a low rate of abandonment. So nobody has to, just each bee does her own thing. She goes there, she assesses its profitability, and she decides, should I recruit? If it's good, yeah, I will, and I won't abandon it. And conversely, if it's deteriorated, I'm not going to recruit anymore, and I will abandon. So each bee, no bee ever has a synoptic view of what the colony is doing, like we have here, but they just follow their rules, and then they achieve a good allocation. Just to remind us, how do the bees recruit hive mates to a food source? They use the waggle dance. Directions indicated by the angle of the waggling, and the distance is indicated by the duration of each waggle run. Now, the reason I show this slide is because I need to explain, how do the bees adjust their recruitment? What do they do if they want to recruit strongly for a food source or not, maybe only weakly for a food source? The key thing that they do is they adjust the duration of the waggle dance in relation to food source profitability. And by dance duration, it's simple. They use a very simple system for modulating the strength of their waggle dances. They just change the number of dance circuits they produce. We looked, there is another possibility. They're adjusting the vigor of each dance circuit, but there's no evidence of that. We could find no evidence that they're each dance circuit is done more vigorously. No, that does not appear to be the case. It's just how many dance circuits a bee performs. And so if it's a great food source, she'll produce maybe 100 or more dance circuits, and that'll take several minutes. If it's a poorer food source, she'll do well at the extreme, no dance circuits at all, or just a handful of them. And let me show you the data that clarifies that, or shows that. This was a different experiment, also done at Cranberry Lake. This was a 2-colony experiment. In this experiment, there were 2 colonies, each in a 2-frame observation hive, and the bees from each colony were distinguishable. We had one colony stocked with yellow Italian bees, and the other colony was stocked with carniolan bees, and they were black bees. And we got those colonies, and we got them instrumentally inseminated, so the Italian queen was mated with Italian drones, and vice versa. So this colony was just cranking out yellow worker bees, and this colony had just black worker bees. And both colonies were near each other at the biostation, and the bees from the yellow colony were trained up to the north, 420 meters away. And what we did for this experiment is we would train 30 foragers to go from this colony to go to this feeder, and 30 foragers were trained from this colony to go to this feeder. And we capped it at just 30 foragers. We wanted that stable, because what we were going to measure was how much strongly they recruited. A fixed number of bees would recruit to their food source as a function of the quality of the food source. And what we did in the experiment then was, this was the experimental colony. And by that I mean, this was a colony where during the day, as you'll see, we changed the food source quality. We started low, 0.5 molar, and we'd leave it at that level for an hour, I think it was, or an hour and a half. And then we'd shift up to the next level, 1 molar, then 1.5, then 2 molar, then 2.5 molar. So with this colony, their food source the quality was increased during the day. This was the control colony, and its food source was always an intermediate level, 1.5 molar. Now, why did you think we had the control colony in there? Both colonies were going to be measuring the recruitment rate during the day under each setting of sugar quality. But why do we need a control colony? We wanted to make sure there wasn't another variable playing a role in our results. Might that be? Weather, right. We wanted to make sure that if we saw changes in recruitment rate to the experimental food source up here, we wanted to be sure that change wasn't due to the weather. So we had a control colony where the food didn't change. And if there was a weather effect, it would show up down here. Luckily, there was not many of the days we were able to get through without a weather change, and the control colony told us that. You can see it's a lot of work to do this stuff. You've got to get the right colonies of bees. You've got to go to the right place. You've got to get the right weather conditions. You've got to train the bees out. You've got to get the right assistants. Dedication. And one of the pleasures is actually doing this with the assistants. Heather can share that with you, because these are really, bright young people that are never been up into the woods, North Woods, for example, never worked with bees. So it's like it's all new to them, and they're really excited, just like us, huh? Okay, so that's how that experiment was set up. And this is what the results showed. It's complicated, so let's go through it. What we've got for each of these plots, there's 1, 2, 3, 4, 5 plots. And each of these plots represents this, the duration, the dance duration in terms of waggle runs produced by the 30 bees going to that feeder. So each bee, we recorded one of her dances and plotted it here. And so we start out, and the black, and I'm just going to show you, these distributions just relate to the colony with the yellow bees, the experimental colony. I'll come back to the control colony in a bit. You could see that when the food quality is low, it's 0.5 molar, nobody danced. Everybody's recording of her dance activity was zero waggle runs. Okay, and that was what we recorded from 9:15 to 10:15. At 10:15, we bumped up the sugar solution, and then we recorded the dance activity of the 30 bees. And now you can see that still most of the 30 bees did 0 waggle runs, but there are a few bees that started to do short dances with maybe up to 10 dance circuits. Okay, that went to 11:15. Then we changed the sugar solution at 12:15, and we left it at that setting for just 30 minutes. And now the bees are dancing more. Now we're up to some decent food quality, profitability. Still some bees doing 0 waggle runs as they did a dance, but there's a few bees that are getting out here doing maybe up to maybe 20 dance circuits when they performed a dance for that food source. Okay? Next time slot, it's 2.0 molar. Now there are very few bees doing no dance circuits at all, and there are a few bees that are quite stimulated by that richer food, and they're out here at 60 dance circuits when they did their dance. But still a lot are down here. And here we are at the highest setting, 2.5 molar. And now there's almost nobody that doesn't dance at all. Almost everybody dances, and many of as you can see, the distribution is shifting to higher and higher durations of dancing, more waggle runs per bee. So during the day, as the food quality went up, the duration of the individual's dances that they performed increased. Now, was that because the weather was getting better or something like that? Well, that's where the control colony comes in. That's what we're going to shift over to this side of the diagram. These black bars, well, there's here, 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 here. Those indicate the recruitment to the feeder, bees per 15 minutes at each of these settings. And now, for the first one, nobody danced, so there's no recruitment to the experimental feeder. In this time period, there's a little dancing, there's a little recruitment. And the last time period for the yellow colony, there's a lot of dancing and the recruitment is high. The critical thing is these white bars. These show the recruitment by bees to the feeder of the control colony. And remember, the control colony, its feeder was always loaded with this intermediate quality food, 1.5 molar. So they always had some dancing, and it was always intermediate, and it was stable. It was virtually rock steady all day long, which told us that the weather was constant. There wasn't some extraneous variable that explained this rise in the recruitment and the dancing during the day. It was because the food quality was going up. So, and we learned from this that yes, the bees turn up the number of dance circuits they produce when they do a dance in relation to the food quality, and I won't go through the details, but that's the only thing about their dance that changes, just the number of circuits. It's very simple. And what happens when you do 20 dance circuits or 50 dance circuits instead of 20? Well, a lot more bees can follow get your message if you're doing 50 dance circuits, because when a bee follows a waggle dance, she only needs to follow about 5 dance circuits. So if you're doing 50, you're creating a dance that when you do a dance, a couple of bees at a time can be acquiring the information from your dance. So if you do a dance and each bee follows about 10 dance circuits. So if you do 10 dance circuits, there's only 2 or 3 bees that are going to get the information from your dance. But if you do 50 dance circuits, then it's 5 times that, so 10 to 15 bees that are getting the message from your dance. So it's a very simple but effective way to modulate the strength of the recruitment. Just change the number of dance circuits you do. More bees will get your message, will have an opportunity to get your message. So the richer the food source, the more waggle runs produced per dance, the more recruits activated per bee. And one thing I want to stress here is that the bees don't have to compare food sources to know what strength of dance, waggle dance to produce. Evidently, they use a built-in scale of goodness. They go to a food source, they experience its profitability, and here the story gets a little murky. We're not entirely sure how they measure profitability, but they get a sense of that, and it's as if they have this internal standard of knowing that this experience is a 10, is a top quality food source. This is only a 5 intermediate, or this is a 1, not good at all. So they go to that, they get a sense of that, and then they come back and dance accordingly. It's a little more complicated because it's also adjusted by how much nectar's coming in. But that is the heart of it. They don't have to compare food sources. They use a built-in scale of goodness. And so if we come back to this problem, this is how they solve this problem. And again, the problem is to get an optimal orchestration of foragers among flower patches to maximize total nectar gain. And what do? The forager goes out, she judges the profitability of the flower patch she's working, and she adjusts her waggle dance duration when she comes back to the hive. The unemployed foragers choose a dance chosen at random. So the bees that do long dances just by chance, even though the bees are sampling the dances in the hive at random, more bees will get their message. The longer the waggle dance, the more followers, and the stronger the recruitment. And as we've seen, if the patch becomes unprofitable, the forager can go, in the extreme, will just quit the patch, and that will end the recruitment of that food source. And it means that as the patch quality goes down, then bees leave the patch. So there's both of these processes, recruitment to build up bees to the patch according to the goodness of the patch, and then there's also abandonment of flower patches according to the goodness or profitability of the patch. And so no bee has to have a synoptic sense of what the landscape of foraging opportunities is. Just if every bee works with a little bit of information, adjusts her recruitment, adjusts her abandonment, things work out. Now, why is this actually so interesting or useful? Well, the whole internet server industry has to solve the same problem as the bees do. Let's think about what I mean by this. You know what a server farm is? This is one of these places that has thousands and thousands of server computers, and they're dedicated to handling internet traffic. And basically, companies like banks or CNN or something like that, they don't have their own servers. They just contract with these server companies. And the server companies, they adjust the number of servers. Let's see if I walk through this better. Okay, yeah. So in these server farms, there are ensembles of end servers. And if you can think of one of these buildings that's holding lots or hundreds or thousands of server computers, that's like a beehive. A colony of bees holds an ensemble of some number n of nectar foragers. So in the internet problem, or the unit of orchestration is a server. In the case of the bees, the unit of orchestration is a forager. In the internet service application, there is a value per request, say from CNN, so many dollars per request, or fractions of dollars actually, a few cents, per request. So if they fulfill, or if you click on CNN on your computer, you're making a request to go to that site. And to do that, you have to your request is routed through one of these servers, which has the information from CNN, for example. And the server farm gets paid per request. And so there's an internet service application, has a dollar value per request, And the analogy with the bees is the flower patch has a profit per foraging trip. So so every time the server provider fulfills a request, it gets paid a certain amount. Every time a forager goes out and works a flower patch, it gets paid in a certain amount in terms of the nectar. And both of these, here's where it gets particularly more interesting. We've seen with the bees that the allocation process is based on advertisements on a dance floor. Well, in these server systems, they also use an advertisement board. And the way this works is, if you're a server and you're feeling like you've got an internal standard of profitability, if you're not getting paid very well, you will consider looking for an alternative place to work not for CNN, but to work for, goodness knows, Fox News. And you will go to the advertisement board because the successful servers, all the servers are posting what their current profitability is. And so if you're a server and you're not getting paid very well, you will look to the advertisement board and you will see, oh, there's better opportunities over here. So these advertisements vary in length according to the dances varying, and just like the dances vary in length. The richer the food source, flower patch, the longer the advertisements last. Likewise, these advertisements on the server board, advertisement board, vary in length. And in both cases, and this is really important, there's a cost to switching. So a bee can't willy-nilly switch from this flower patch to another. So for the bee, the cost is that she has to, if she's stopping working this patch of flowers, she goes back to the hive. She has to follow a dance. She has to find the new patch of flowers. With the server, the cost is that it takes about 10 minutes. When you switch from working for CNN to working for a bank, for example, the server has to clear out its memory. It takes about 10 minutes per server to clear out its memory. So that's 10 minutes of downtime where it's not handling any traffic and it's not generating any income. So the servers don't switch willy-nilly from one application to the next, just like the bees don't switch willy-nilly from one to the next. But in both cases, there's nobody overseeing this thing. It's just a distributed means of getting the right allocation by individuals referring to an internal standard of profitability and deciding to look around. If your sense of profitability is low, and you factor in the cost of making a switch and you decide to switch, then you just sample on the advertisement board and then you will switch your allocation. Now, the algorithm that is used to implement this allocation of servers among websites at internet hosting centers is based on, they read about what we had learned for the bees. And in respect to our analysis, they call it the honeybee algorithm. And it is remarkably close. And the reason they know about this is there was one gentleman, Sunil Nakrani. He was from Oxford University. He came over to Georgia Tech, and he met my colleague who had worked with me in the bee analysis, Craig Tovey. And and Sunil was looking for a postdoc project. And he came over to Craig, because Craig's a very creative guy. And Sunil, they just got talking, and Craig was telling him about, well, we did this project with the bees, and it works like this. And then Sunil started asking questions. Well, what about this? What about this? Because Sunil was thinking about this internet hosting problem. And then they realized, oh, the problem is so similar. And then once Craig explained how the bees do it, Sunil started writing the program, this honeybee algorithm. And that's what's used today by most of these internet hosting centers. His honeybee algorithm, their honeybee algorithm has boosted the revenue by 10 to 20%. And the 10 to 20% of $50 billion a year industry is what? That's $5 to $10 billion a year. That is, the value of this HBA per year is equal to the more than the budget of the U.S. National Science Foundation, which is about $7 billion a year. And alas, the engineers, and me too, kicked themselves for not patenting this thing. And that's just the life. So anyhow, that's what it is. And that's why I say this is the most valuable thing. And it's now highlighted by our National Science Foundation. The honeybee algorithm is highlighted as a wonderful example of the demonstration of the value, the monetary value of basic research. It's a great example. So just to recap, we have looked at a beehive as an information center. The colony, the whole colony, collects and uses information about patches of flowers. And we've seen that how a colony solves this problem of allocating its foragers among sources of nectar works by this, what we call now the honeybee algorithm. Each bee goes to her place, adjusts her reporting on her site accordingly. That will recruit more individuals to that site if it's high quality, and bees will leave working at that site if it's low profitability, sufficiently low to cope with the costs of making a switch. Oh, if you would like to read more about this, there is a book that I wrote. This is the book I'm probably proudest of because it is the most sophisticated book that I've written, called The Wisdom of the Hive. Alas, it's very expensive, but if you maybe the club will have a copy or something like that. I will never use this publisher again, but it's a good read, especially if you like thinking about this sort of thing. Distributed, decentralized control, how to make a whole system work well. So, thank you for, again, your interest and attention.
When you did your tests with adjusting the sugar content, did you also do any tests adjusting the travel benefit? If you had 30% close to the hive,
right,
and you had 65%, let's say 2K away,
yeah,
and then you put 40% in between,
yeah,
there must be a point at which
yeah,
they will not go to the 65 because the travel distance is costing them energy.
Yeah, that's right. Yeah, when the bees factor the profitability, they do factor the distance, the flight, because that's one of the costs. And we have done experiments that have looked at that. And yes, what you can in fact titrate. You can do exactly as you suggested. You can make this feeder have a richer sugar solution, but you can make it more distant. And then you can actually, by moving it out step by step, you can find the point at which the travel costs cancel out the higher benefits of that richer sugar solution, so the recruitment rate is the same for both feeders. And yes, and that is part of the real world problem for the bees. The distances vary, the sugar concentration varies, the nectar availability varies, all of those things vary. In our experiment, we pared it down. The two food sources were the same distance, they both provided food ad libitum, but their sugar concentration was different.
How did you keep the black bees from shooting up to the other hive?
Oh yeah, thank you. I forgot to mention that. What we do is we've got we cap it at 30 bees, and the way we do that is when a new bee shows up, not one of the 30 designated bees shows up at any of those feeders, we take a little Ziploc bag and put it over the bee, and then the bee will crawl up into the bag, and then we can zip the bag shut. And it doesn't, so there's no killing of the bee, so there's no release of alarm pheromone. The bee is not freaked out, but she is removed from that operation until the end of the experiment. And we didn't want to kill these bees because they were labeled. We worked hard to get the colony. and they can, as long as you keep the little bags out of the sun, they will be fine for several hours because they've got food in their stomachs. Yeah. Thank you for that question. Yeah, there's a lot of little techniques to make these experiments work.
My question's not quite as good as David's, but I've got two. If you're talking about the cost, are there still scout bees going out at the same time of maximum foraging at any one site to look for alternatives? And my second question is, have you done, or were you able to do similar studies or research on new home sites. Do you remember you talked about swarms and
Yeah.
finding new home sites?
Yeah.
Could you do similar studies on how do you find a new house?
Yeah.
Thank
yeah.
you.
That's a whole nother story. And that I did this work before I did the swarm studies because the logic is really the same, though the rules of how they work are tweaked, because in the home site situation, they don't want to distribute bees among nest sites. They want to get the bees focused on the best one. So there are some differences, but there are many, many parallels. I started with this one. This is actually easier to investigate than the house hunting because the bees, they'll forage all the time. And so you can really just keep watching the process. It's a never-ending process. But so yes, we did that. Your first question was about no, what was the first question? Scout bees. Yes, there's always scouting going on in the background. And that's right. And that's a key part of any foraging operation. You've got I like to call it, what I talked about was the exploitation part of known food sources. For a colony to persist and keep tracking the environment, it has to also have a exploration component. So it's got scout bees always out looking around. Now, we dodged that complexity by going to the Cranberry Lake Biostation. There were scouts out there, but they weren't finding anything. And I thought you were going to ask, well, what if a yellow bee showed up at the black bee feeder, or vice versa? There was a very low level of that, but we could then. That's where the Ziploc bags came in again.
Going back to the dance floors, because you did your observation hive as basically a 2D hive, and when we learn about the brood, it's basically rugby-shaped, sliced through all the frames. How does that translate? Because in America, you mainly use Langstroth, and they're what we call cold way. And here, because we're using nationals, or most people are using nationals, and it's the warm way, how does that dance floor translate across a 3D system rather than a 1D?
Yeah. Basically, you can think of this as just a slice through a three-dimensional nest. They organize it. What I showed you there would be just like one slice, one comb through a 3D nest. So they keep the same organization, but they don't have the luxury of having parallel frames. Spreads out a little more across the frame, perhaps. Yep. Well, for the bees, certainly having multiple combs so they can thermoregulate and be more compactly oriented. Oh, cold versus, who knows? If you ask the bees in nature, what do they do? When I look at the naturalness, I see all ranges. There's no fix. It's not one way or the other. They seem to adapt more to the particulars of a site.
How does it actually work when we whack a feeder on top then? Because obviously, when we put a feeder on top,
when you put a feeder,
is it still done through the waggle dance? And given that they're not going out, obviously, how do the bees communicate that food is actually just upstairs in the loft?
Yeah, that's a really different situation, obviously. And the bees that go and unload the food from the feeder are the nectar receiver bees. It's not the foragers going up there. We wondered about that too, and it's very easy to see that with an
How do they know it's up there, though?
Somebody finds it, and I think it's just we put scent in our food. Little by little, other bees will find it up there. But we know from our experiments, many experiments where we have got the bees labeled to go out to the feeders, like at Cranberry Lake, where we know who they are. Those bees that are going to our feeders are not going up to a sugar water feeder on top of the hive. So yeah, it's because we could talk all day about this, but those middle-aged bees that are the nectar receivers, that's one of their workspaces, the honeycomb areas up there. That's where they truck between the entrance where they're receiving nectar and taking it up to the honeycomb. So when you put a feeder up on top, that's right in their work area, workspace.